Okay, we are on live on YouTube. So. Perfecto, gracias, Fernando.
All right, I think it's time to get started. Greetings, everyone. So welcome back to the second day of an Invisible21 workshop. So my name is Tao Han from the University of Pittsburgh, as you can see from my virtual background. So today, this morning, my morning here, we will have two plenary talks and plus one student forum. So the plenary talks will be 30 minutes, including Q&As. Okay, So I would like to remind the participants to try to turn on your video so that we can make you visible in our Invisible21 so that people can see each other. So without overdue, let's start our academic session. So the first speaker will be Eligio Lisi. He's going to tell us about the neutrino mass mixing parameters circa 2021. Eligio,
Okay.
please take the floor over.
Okay, thank you very much. Let me share the screen and start the presentation. Okay, I think you can see it now, right?
Yes, we can.
Okay, so I would like to thank the organizers for inviting me to this very interesting workshop. And so what is the outline of what I'm going to say? I will be talking about knowns and unknowns in the mass mixing neutrino framework. The known parameters, the two squared mass splittings and the mixing angles are already in our hands or in the hands of this bear. There are some unknowns that we are smelling in a sense, but are not really in our hands yet. And maybe there are some issues affecting both known and unknown parameters. I will not be talking about beyond standard model and three neutrino framework that will be covered in a subsequent talk. So this talk updates a paper that we wrote last year, and actually a more complete analysis will appear soon. So what are the parameters we are talking about? Well, as you know, yesterday you heard about the CKM matrix. We have in the neutrino sector a PMNS matrix parameterized in terms of three mixing angles that we call θ23, θ13, and θ12, plus a CP violating phase delta, and if neutrinos are Majorana, two extra phases. Concerning the masses, well, we don't really know the absolute masses, except for the fact that they must be below 1 eV and possibly much below 1 eV. But we know two squared mass splittings that I will call small delta m square, this one, and the big one can be conventionally defined in different ways. I will use the following: the average of delta m square 32 and delta m square 31. And which distinguish normal ordering if this big delta m square is positive, and inverted ordering if it is negative. Of course, oscillations depend also on extra energies due to interactions in matter, but oscillations are not sensitive to the absolute neutrino mass scale. Well, as you know, beautiful oscillation data have established this three neutrino framework in different oscillation channels, both survival or disappearance channels like nu-E in Camland and solar neutrinos at a given frequency of oscillations, at another frequency in short baseline reactors. But also we have learned a lot from nu-mu to nu-mu oscillation in atmospheric and long baseline accelerator neutrinos, and also in the appearance channels, especially at accelerators. Now, what is important to notice is that these experiments are sensitive to at least one delta m square and one mixing angle, possibly two mixing angles, like in this case, dominantly. And each leading oscillation parameter has been tested by at least two classes of different experiments. And this allowed various tests of consistency and between different experiments that have been crucial in establishing this framework. Now, most of the action now is on subleading effects, namely not on these dominant oscillation parameters, but on subleading oscillations that may be sensitive to CP violation, to the difference between normal and inverted ordering. And this is going on especially in the nu-mu to nu-E channel in long baseline accelerators. Now, it is useful to analyze oscillation data in the following sequence. First, starting from long baseline accelerator, solar and Camland data, which are sensitive to all the oscillation parameters at the same time. Then one can add short baseline reactor data that are sensitive to the big delta M square and theta 1,3, but affect also the other parameters through correlations. And in the end, one can add atmospheric neutrino data, which are very rich in content, in oscillation information, but the information here is very entangled. And concerning statistics, what I'm going to show is a series of bounds and contours in terms of number of sigma, where number of sigma is the square root of delta chi square. And it is understood that by projecting allowed regions at n sigma onto one parameter, you get the n sigma bounds on that parameter, the other being marginalized away. Now, single parameter bounds n sigma versus one parameter would scale linearly and symmetrically in the limit of Gaussian errors in both normal and inverted ordering around their best fit values. But in general, one ordering is preferred over the other, so it happens that some of these curves will be shifted in one sense or another. Now, let's see the results, starting by the unknowns, the thing that we know less, namely the phase delta, the ordering, and also the octant of theta 2,3 if theta 2,3 is smaller or bigger than 45 degrees. So let's start with a minimal set of data, long baseline accelerator, solar and CAML, and this is n sigma versus delta and versus theta 2,3 for normal and inverted ordering, the blue and red curves. And you can see that inverted ordering is favored actually at 1 sigma by this data set, and the phase delta for inverted ordering is preferred to be around 3 pi over 2, so maximally violating CP, while in normal ordering is close to 1, so consistent with CP conservation. And you can see that you can flip between the first and second octant at less than 1 sigma, so basically you are degenerate in this case. If you add the short baseline reactors, now an interesting thing happened. Normal ordering is now favored at 1.5 sigma, so the curve that goes upward is the red one. And delta is still preferred to be CP violating in inverted ordering and CP conserving in normal ordering. And there is a slight preference for the second octant. Finally, if you add the atmospheric neutrinos, this is still without the latest atmospheric neutrino data, normal ordering is favored almost at 3 sigma, and delta is more or less the same, and the second octant is also preferred. But this indication is actually fragile because the latest Super Kamiokande data, which are not yet included in these slides, may flip the preference for the first octant. Now, if we want to look at all the parameters at the same time, this is the number of standard deviation as a function of the 2 delta m square, delta, and the 3 mixing angles. And you can see that on this part of the plot, you have almost linear and symmetric errors. So these parameters are measured very well. Theta 2,3 is also, I would say, measured well, but not as well as the others because of this octant degeneracy. And concerning delta, you can exclude something at 3 sigma, but not really say if there is a solid indication in favor of CP violation or not. Of course, you know that other groups are also making global analysis of oscillation data, like what can be called the NuFit group and the Valencia groups, and this is a comparison in the same graphical representation. There is good agreement between all groups. I would say the best agreement we find with the NuFit group. But in general, I would say it is excellent given the fact that these are independent analyses. Now, if you want to translate the previous figures into numbers, you get this table. I would like to focus only on the last column, which is the fractional precision for each parameters. And you can see that it ranges from a minimum of almost 1% for the big delta m square to a maximum of 5% for sin squared theta to 3. Now, I would say that I'm a bit scared by a formal uncertainty as small as 1% for the big delta m square for reasons that I will discuss in a few minutes. Now, we can add some questions about these results. So why adding short baseline reactors flip the preference from inverted to normal ordering, as these data are not sensitive by themselves to mass ordering? Concerning the parameters which are not yet measured, the delta, the ordering, and the octant of theta to 3, they are all entangled in nu to nu oscillation. What are specifically accelerator data telling us in this channel? And as I said, can we really be confident about 1% formal accuracy on delta m square? I would say that the answer requires now integrating different pieces of information: the covariance of oscillation parameters, the complementarity of different experiments, and maybe further collaboration between experimentalists and theorists. Concerning pairs of parameters, the covariance of parameters, I will show only two ones for lack of time, namely the covariance between the big delta m square and theta 2, 3, and the small delta m square and theta 1, 2. Concerning delta m square and theta 2, 3, let's start again with the minimal data set for normal ordering on top, inverted ordering on the bottom. This is the usual delta m square versus sin square theta 2, 3 plot, where you can see the two degenerate solutions. And notice that the best fit value of delta m square from long baseline accelerator data is below 2.5 10 to the minus 3 v square. Now, what happens if we consider standalone reactor and atmospheric neutrino data? Standalone reactors are not sensitive to theta 2, 3, so they would give just a horizontal band. And you can notice that the best fit of delta m square is higher than for long baseline data, while for atmospheric neutrinos is consistent with long baseline accelerators or even a bit smaller. Now, the relative difference between the delta m square of reactors and the others is lower for normal ordering and also for non-maximal theta 2, 3 mixing. So what happens when we combine everything together? Since we have a small and a large value of delta m square, the final fit is somewhere in between. But what happens is that since the difference is larger in normal ordering is preferred, even if short baseline reactors are by themselves not sensitive to the ordering. And this goes under the name of accelerator reactor complementarity or synergy or whatever you may call it. And also you have further indication for non-maximal theta 2, 3 mixing. A case in which there is instead very good agreement between different data sets is solar neutrinos in Camland. As you know, until a couple of years ago, there was some tension between different values of the small delta m square of solar and Camland neutrinos, but with the latest Super Kamiokande data, this tension has been resolved and actually there is a very good agreement at the level of 1 sigma. Unfortunately, I would say because the tension might have pointed to new physics in solar neutrinos. Are there some issues in this picture? Of course, yes, from time to time there are theta tensions and that capture our attention. And now the most important one is between the two long baseline accelerators that are running, T2K and NOVA. They find some differences in the nu mu, nu e, and anti-nu mu to anti-nu e appearance that blur the preference for normal ordering and for CP violation that was stronger 2 or 3 years ago. So I will show some details, if you want, for experts in the form of B-event plots and make some very general comments that everybody can appreciate about possible synergy between strong and electroweak physics. So what are these B-event plots? These are not used in fits, but are useful for graphical purposes. So we can plot the antineutrino and the neutrino total number of events in T2K here and in NOVA here. This is just the number of events in each axis. And the gray bands and the ellipse are the data. And these colored ellipses are the predictions for normal ordering in blue, inverted ordering in red, and the thick one for second octant of θ23, and the thin one for the first octant, and also with some specific values of delta plotted on the ellipses. Now, the main one needs to study these figures for a couple of minutes to understand what's going on. The main message is that taken alone, T2K prefers normal ordering, and also NOVA prefers normal ordering, namely the blue curves. They have a somewhat different indication for delta and also very weak indication about the octant. But the main message is that both prefer normal ordering. Now, we can rearrange exactly the same information in a different way. Namely, instead of plotting T2K and NOVA separately, we separate neutrino and antineutrino. So T2K antineutrino versus NOVA antineutrino, and the same for neutrinos here. So this is exactly now the same information as before, but plotted in a different representation. And now it turns out that the preferred curves are the red ones, namely inverted ordering. So separately they prefer normal ordering, but in combination they prefer inverted ordering, and in this case CP violation, while they still give different answers for the octant of θ23. So what is the message? Of course, there is something not really working. There is some tension that makes the results unstable. This is just one way of showing that they are unstable. And so the current unknowns, the ordering, the octant of θ23 and the CP phase delta are in a sense blurred by this tension. Now, further data may tilt the current balance or even point towards new physics, for instance, non-standard interaction. I would say it's a bit difficult that T2K will change radically because the data are already at the extreme of their azimuth sensitivity, while in NOVA the situation is much more fluctuating because all these colored ellipses are within 1 sigma of the data. And certainly we will learn more from a joint analysis. Now, the question is there only statistics behind the T2K and NOVA tension, something that we just solved by more data? Well, in my opinion, not, because there is a delicate interplay, as we have seen, between both the big delta M square and θ23, two known parameters, and the three unknowns. And there is a general issue that affects all of them at the same time, namely that neutrino interactions in nuclei are not understood as accurately as desired. We know, but we don't really dominate the physics of neutrino interactions in nuclei. It's not an easy process. Initial effects, final state effects, and intermediate interaction make it complex. There are relatively few data, especially on total cross-sections, but very sparse on differential cross-sections. So there is a great effort to improve the situation, but non-negligible uncertainties remain. And just to make an example, you can see in these papers, you can try to make the following exercise. You make synthetic experiments, you generate data with one model for the cross-sections, and you analyze them with another one. Be it GNE or GBU or NEWT, these models used in long baseline accelerator experiments. You can see by doing this exercise, you can easily bias the oscillation parameters both the known ones and delta CP, I mean, the still unknown ones. And the effects, of course, are reduced by tuning the models to near detector data, but let me remind that no model currently explains all the available cross-section data. So the current 1% global fit accuracy on delta M square, in my opinion, might be a little bit optimistic, and things might change as we learn more on cross-sections. And there is a more general problem, I would say, is that strong interaction effects on weak interaction physics are ubiquitous. They appear in atmospheric neutrinos, in the cross-sections at GeV energy, as we have seen, but also, okay, at very high energies and at extremely low energies like those tested in neutrino-less double beta decay. I would call this vast field electroweak nuclear physics, and I think that we have to support any initiative that bridges the experimental and theoretical communities into this interdisciplinary field, because it's really crucial for the advancement of neutrino physics. Finally, the last few minutes, I would like to comment about absolute neutrino masses. As you know, we have only 3 ways at present to access the absolute masses: beta decay, neutrino-less beta decay, and cosmology, probing different combinations of the masses. And even if you don't know anything about these experiments, oscillations in the plane charted by any 2 of these 3 observables constrain the phase space to be within these very narrow bands for normal ordering and inverted ordering, where the largest uncertainty is actually due to the unknown Majorana phase. Now, actually, we know something in this plane, but only in the form of upper limits. It's very reassuring that Catherine, just a few weeks ago, has presented the first sub-EV upper bounds on M beta. We also have an order of magnitude below some upper bounds from neutrino-less double beta decay experiments, and also with some very large uncertainty, upper bounds from cosmology that I would say range from aggressive ones around 0.1 EV to more conservative ones, a few times this upper bound. And of course, cosmological data are putting pressure, as you can see, on inverted ordering, but now people are more appreciating more the fact that there are tensions also in cosmological data. So I think we are living in an interesting period, and we should pay more attention to the tension in the cosmological data and how they can affect the upper bounds on neutrino masses. Indeed, if we take all the data at face value and, for instance, want to know what they are telling us about the unknown that we are smelling better than others, namely the mass ordering, if we calculate the delta K square for different scenarios, well, oscillation data prefer normal ordering, as I said, at a level of around 2.7 sigma, although long baseline accelerator actually prefer inverted ordering. Cosmological data may add a contribution which goes from 0 to a couple of sigma, depending on the scenario that you consider. And if you put everything together, you get something which is around 3 sigma. And as I said, we are actually working more on the conservative cosmological cases, which tell us less on the mass ordering, but maybe more on absolute neutrino masses. So I think I'm going to the summary of my presentation. As you all know, just before 1998, we were still thinking in which direction to go beyond the standard model, but neutrino oscillation told us that there is at least one tree growing beyond the standard model, and in our hands or in the hands of this bear, there are already 5 parameters which were thought to be 0 and now are measured with an accuracy of the order of the percent or a few percent. And this is the 3 neutrino oscillation 3, if you want. And of course, we are smelling the unknown parameters. Maybe we have some indication, although not compelling in favor of normal ordering. Still, we don't know delta CP, and the octant of θ23 is an annoying ambiguity. And it's difficult to get our hands on the absolute neutrino mass, and especially on the Dirac-Majorana nature of neutrinos. And of course, we would like to see if there is anything beyond this augmented standard model with massive neutrinos. But this will be matter for some invisible workshop in some future year, where maybe we will have our hands on these unknown parameters and start to smell physics beyond the standard model and beyond 3 neutrinos. So thank you for your attention.
Thank you very much, Eligio, for this very nice talk. I think we can open for questions. So please use a raise hand button to ask questions. So the first one actually came from Albert Joe, who could not raise his hand, but he would like to ask a question. Albert, could you take the floor now?
Yep. Hi.
Hi.
So I wanted to ask about your comment about the cross-section and biasing. So I guess there are two kind of aspects. Firstly, I mean, so the collaborations provide some kind of systematic uncertainty to their prediction about the unknown cross-section. So do you think that could be, was your comment relating to the fact that that uncertainty may change if you include data not just at their near detector, but a kind of global analysis? Or did you mean that in the global fits there is no systematic effect on the prediction?
Well, thank you for this. Allows me to clarify one aspect. I'm not claiming that the collaborations are underestimating the errors, but there is a problem when you combine data from different experiments. For instance, data from Super Kamiokande atmospheric neutrinos, T2K, and ice cube all depend on neutrino cross-sections on a water target, okay? When you combine all this data together, you cannot really separate this common uncertainty. This is a common systematic uncertainty. And by merging all the data together, you are hiding the fact that this is common. And so if you have, for some reason, a 1% shift in the reconstructed energy, which is common to all these experiments, you are going to reduce it in the global combination, because you have no way to isolate it in the way global analysis can be done at present. So in the end, you put together several data from different experiments, but you have no real way to separate the common systematics at present. So I would say that it is very important that the collaborations get together. For instance, for atmospheric neutrinos, it would be nice if Super Kamiokande and ice cube get together and use a common model for the cross-section, a common model for the original neutrino flux, and so on and so forth. Otherwise, by combining them at face value, the final uncertainty will be reduced. And this, I think we are approaching a situation where this is dangerous.
Well, Eligio, thank you. So in terms of time, we may have to move on to the next question. So next question is from Ivan Esteban. So Ivan, could you, go ahead.
Okay, thank you. So thank you for the next talk, Eligio. I have a very quick question. So you showed that there is a small preference in cosmology if you use, I think, that the most aggressive data set towards normal ordering. And I was wondering, where does this come from? Is this because of some volume effects in the priors, or is the data really pointing towards normal ordering?
Well, it's both. Well, the main effect is that in general you can reach a better fit in normal ordering than in inverted ordering, just because you have very little phase space left. Not in terms of priors, because we are not using a Bayesian analysis, but a frequentist one. And also there is a very small difference between normal and inverted ordering, because but at the level of a small fraction of delta K squared, because cosmological data are not exactly sensitive to the sum of neutrino masses, but also to a lower extent to how they are distributed, if in normal or inverted ordering. Now, of course, you will distinguish the two orderings by cosmology only when with future data that will have much lower uncertainties. At present, I would say what I find it most interesting is this question of tensions in the cosmological data sets. The most known one is the Hubble tension, but there are others, and how they affect the upper bound on neutrino masses. I think we should not stick to 0.1 EV. We should be perhaps more conservative and wait for laboratory data to confirm any possible future signal from cosmology.
All right, so in the interest of time, I think we need to move on. So let's join me to thank Alijo again. Thank you very much.
Okay, thanks.
Yeah, so the next item is a PhD forum. So we have 5 short talks, and each talk is 5 minutes plus 1 minute question. So let's move on then. So the first talk will be given by Gabriel Soya, and the topic will be an on-shell perspective on neutrino oscillations and non-standard interactions. Gabriel, please go ahead. You have 5 minutes plus 1 minute question.
Can you hear me?
Yes.
Okay. So, hi everyone. Today I'm going to talk about a bit of this project I worked on, which is in essence the application of a new theoretical technique to neutrino oscillations. So the basic idea of this project was to apply on-shell methods to neutrino oscillations. And although the on-shell formulas is not very well known yet, it can offer a new and complementary approach compared to the usual ones of quantum field theory and quantum mechanics. So the main features of these formulas are the following. First, there are no fields nor Lagrangians. We only write down physical amplitudes by relying solely on principles like Lorentz invariance, unitarity, and locality. The only inputs we need to write them down are the particle spectrum and the symmetries of the theory. One of the special things about on-shell methods is the fact that we can completely fix on-shell 3-point amplitudes from Lorentz invariance and unitarity alone. So in the case of neutrino oscillations, one relevant amplitude to us is the neutrino charged lepton double amplitude, and it is completely fixed from these first principles. It is already worth mentioning here that this amplitude is also a tensor in flavor space, as it depends on both the flavor of the neutrino and of the charged lepton. Well, but since this amplitude is fixed from first principles, it will actually contain all possible effects coming from new physics. And this last point can be seen more clearly from the connection between massive low energy amplitudes and massless high energy ones. By taking the high energy limit of massive amplitudes, we can recover several massless amplitudes from the unbroken electroweak phase. And some of these amplitudes, some of these massless amplitudes will be related to the renormalizable interactions of the standard model, while others will be related to effective interactions. From this matching with the renormalizable standard model, we can recover, for instance, the PMNS matrix as a coefficient of the massive amplitude. And it is important to notice here that this PMNS matrix is not obtained by diagonalizing a mass term, but only by inspecting the flavor structure of the amplitudes. On the other hand, from the matching with the effective operators, we find out that all coefficients of the massive amplitude are in fact an infinite series in the cutoff expansion. And even more, the massive amplitude is taking into account different EFTs at the same time. And the two relevant EFTs for us in this case is the SMAFT when neutrinos are Majorana, and the NuSMAFT when they are Dirac. Therefore, 3-point amplitudes computed from on-shell methods will contain all possible effects from new physics from effective operators and at all orders in the cutoff expansion. So you can see how powerful this formula is. Well, but to actually compute an oscillation amplitude, we need to glue two amplitudes together, one for the production and one for the detection of the neutrino with a propagating neutrino in the middle. And this can be done, at least at 3 level, through polology. So our oscillation amplitude, which in this case is a 4-point amplitude, will be given by the product of production and detection amplitudes times a near on-shell neutrino propagator. And as I was saying before, all effects from new physics and effective operators are included in the sub-amplitudes, which are the production and detection amplitudes. And one of the most important aspects is that these effects are parameterized only by a finite set of unknown parameters. And this is, of course, the main result of this project. Well, and to conclude, we see that on-shell methods can indeed provide a new perspective on the phenomenon of neutrino oscillations. This set of techniques relies strongly on the most basic physical principles, making it very appealing from the theoretical point of view. From the phenomenological point of view, the fact that low energy amplitudes are a no-order expansion, the EFTs, is crucial and allows us to make more general predictions beyond the standard perturbation theory. Well, I finished my presentation here. Thank you very much.
Thank you very much, Gabriel. So I have time for one question. Anyone, please raise your hand for the question. Yes, there's one. Thomas, please unmute yourself and go ahead.
Yes, hello. So, I mean, from the practical point of view, I mean, what would it imply? Do you get new expressions for the oscillation probabilities? And in which term would this be or complementary to the usual approaches to look for new physics in oscillation?
Yes, thank you for the question. Yes, in principle, we obtain an amplitude that contains several terms coming from beyond the standard model physics. We cannot make a very one-to-one correspondence with the QFT approach, but we can identify some similarities. In this paper, we actually did not compute the oscillation amplitude because we thought that it wouldn't bring much insight on the final expression. But we can certainly identify which are the new contributions and estimate their effects at order of magnitude. So yes, we can see new effects coming to the oscillation probability, sure.
Okay, thank you very much, Gabriel. Again, let's move on to the next talk. So the next talk will be by Shiba Safak. So the title will be Enhanced Violation of Lagrangian Inequality in 3-flavor neutrino oscillations via non-standard interactions. Shiba, please, 5 minutes plus 1 question.
Hello. Hello, everyone. My name is Shiba Shafak, and I will talk about exploring Lagrangian inequalities in neutrino oscillation phenomena. Now, we know that neutrino oscillation is a result of mixing between the flavor and mass eigenstates. So the effective Hamiltonian for neutrino propagation consists of a vacuum Hamiltonian, an effective Hamiltonian in presence of standard interaction, and an effective Hamiltonian in presence of non-standard interaction. Non-standard interactions are a class of new physics scenarios. Now, Lagrangian inequalities provide a way to test the quantumness of a system. These are based on 2 assumptions. Macrorealism, which implies that a system is at all times in a definite state, and non-invasive measurability, which means that the system can be measured without having any impact on subsequent measurements. Now, to study LGI in a system, we consider a dichotomic observable Q, which can only take values plus and minus 1. Now, measurements are made on the system at times ti, and we consider a two time correlation function, Cij. By a combination of these two time correlation functions, we obtain a parameter K3, which is constrained by the assumptions that we have made. So we obtain an inequality for K3, but for any n, odd or even, in general, we can obtain a Legge-Gerg inequality. So for the systems that respect the assumptions, the classical systems, they would obey these inequalities. But the systems that violate Legge-Gerg inequalities, those systems can only be explained by quantum mechanics. So we also have an upper bound on the value of the parameters. So to explore Legge-Gerg inequalities in neutrino sector, we consider our system to be an electron neutrino. Measurements are made on the system, and if the system is in electron neutrino state, then our dichotomic observable takes value +1 and -1 otherwise. We evaluate the two time correlation functions using joint probability. For two flavor neutrino oscillation, the joint probabilities are used, and the two time correlation function C12 and the LJ parameter K4 are shown, and they depend on delta L, which is the difference between L2 and L1, and not individually on L2 and L1. So for the three flavor case, we have 9 joint probabilities, and these joint probabilities depend on the standard interaction and the non-standard interaction parameters. So now here, we see the interplay ofCijs leading to the overall dependence of K4. C12, C23, and C34 almost coinciding give the curve its overall frequency, and C14 is responsible for the fine features of the curve. Here, the Hamiltonian for neutrino propagation is shown, and non-standard interactions are parameterized in the last term. We consider one NSI parameter at a time, and epsilon E mu and epsilon E tau act in the opposite direction, which is expected from the analytical considerations. Okay, so here the combined impact of NSI terms has been shown for neutrinos as well as for antineutrinos. And with the goal of maximizing the parameter K4, the phases have been appropriately chosen. So here the value of the LGI parameter K4 is shown for various scenarios. And we see that we find enhancement in the violation of LGI parameter in the non-standard interaction case as compared to the standard interaction case. And in any case, the value of the parameter K4 does not exceed the maximum Lurer's bound. Thank you.
Thank you very much, Shiba, for the nice presentation. So we'll have time for one quick question from the audience. So I don't see the hand yet. Second call, any question? Seem to have no more questions. Okay, let's thank Shiba again. Thank you very much. Let's move on to the next. Let's move on to the next talk. So that will be by Albert Zhou. The title is Constraining the Tau Neutrino Transition Magnetic Moment at Dune. Albert, please, 4 minutes plus one question.
Hi, sorry, can you see my screen changing?
Yes, we can.
Great. Okay, so hello everyone. I'm going to talk about constraining neutrino transition magnetic moments at June. This work was done in collaboration with my supervisor Thomas and the postdoc Jingyu, and it's on the archive. So we investigated a neutrino with an additional dipole interaction with a new sterile neutrino or heavy neutral lepton. And this was investigated in the context of the mini Boone anomaly and also Xenon 1T recently. But here we're just going to see, so that's why that's where it's been considered before, but we're just going to see now what we can see at June with this. And so our original idea was that it's difficult to constrain this parameter for the tau because it's very difficult to have an intense tau flux. So we considered the oscillated flux from the neutrinos at June to produce the signal, where the muon neutrinos travel, oscillate into taus, and then upscatter, and then head towards the far detector and leave a decay there, which you can see also in this diagram here. And the signal will then be a photon here. And then we also considered using the intrinsic muon and electron neutrino flux at the near detector. So our signal types outside events where the upscattering occurs outside and the single photon in the detector, but also you can have the upscattering and the decay inside the detector. And then in the incoherent case, you can also see the nuclear recoil as well as the single photon decay. And so these are our results. And so here's the decomposition between each of the targets. So that we can have scattering on electrons or the individual nucleons incoherently or upon the whole nuclei coherently. And as you can see, because the coherent interactions get a boost from the Z squared, it mostly dominates, but the incoherent does dominate at is more significant at higher energies. And we can also see here some decay lengths that I've plotted, which indicate where you can differentiate the two signals in case of the inside events, and also when the outside events become irrelevant. And so here I show the global picture for all the references with the other exclusion curves. You can see our paper. But as you can see, June has comparable sensitivity to SHIP, and for intermediate masses, it's relevant for unconstrained parameter space. And so here's the same picture for d mu, but with extra curves from different experiments and the electron case. So in conclusion, June can set competitive limits for d tau at the far detector with the oscillated flux. And the intrinsic flux can be used to decay the parameter at the near detector. One thing is that we didn't consider meson decay, so direct sterile production from the Lagrangian at the near detector. That's to be investigated. And to get I only show rate 6 events per year curve, but you'd need a proper background study. But fortunately, I didn't mention this before, but the liquid argon detectors will be able to discriminate between single photon events and electron events. So that's a good thing about that. But otherwise, thanks for your attention. And are there any questions?
Thank you very much, Albert, for keeping up time and a nice presentation. So we have time for one question. Please. Yes, I see the hand. Ivan, Esteban, please go ahead, Ivan.
Hi, thank you. So thanks for the nice talk. I have a quick question. So I see that you are considering transition magnetic moments between the tau neutrino and a heavy fourth neutrino. Have you considered transition moments between the light neutrinos, or what will happen in this case?
No, we didn't consider that because I think there are bounds on this already, but no, we didn't consider that. So I can't immediately say what would change in that case.
Okay.
That's all right. We can leave the discussions at a later time. You both can connect. So there's one more question I would like to entertain.
Sorry, they can also use the Slack room to go on discussing. There is
That's
a
right.
Slack room open right now. So
Yeah, thank you very much, Belen. So there's one more question. I would like to entertain this question as well. Iligil, please go ahead.
Yes, I wonder if you can learn something from atmospheric neutrinos, nu tau, at least on a statistical basis, or only at accelerators.
No, yes, of course you can learn something. So actually, this ice cube curve, which was done in 2017 by Colin et al., considers this, but they consider what they call double bang events, which is what we call inside events, where you see both the nuclear and decay. But that's an open question, which may or may not be answered in the near future. But that's a good question.
All right, thank you very much, Albert, again. Let's move on to the next talk. So next talk will be given by Manuel Gonzalez Lopez. So the title will be GeV scale neutrinos, meson interactions and dune sensitivity. Manuel,
yes,
please take
can
over.
you hear me and see my slides?
Yes, we can.
All right, great. So thanks. I'm going to talk about GeV scale neutrinos. Of course, we need to extend the standard model to account for neutrino masses. And the simplest way to do so is by introducing right-handed neutrinos or heavy neutrinos or heavy neutral leptons, whatever you want to call them, which are going to be a part of the flavor eigenstates by an enlarged mixing matrix, this U matrix. So now the heavy states and the light states will mix, and this will allow us to probe experimentally heavy neutrinos. Of course, their mass is going to be possibly lying on very wide energy ranges from the electron volt to the GAT scale, and the associated phenomenology is going to be very different. We'll be working in a minimal extension of the standard model with no extra interactions, and thus the heavy neutrinos will be singlets and will only interact with standard model particles via mixing with the light states. The mass and the mixings of the heavy neutrinos will be the only relevant parameters. And of course, we need to introduce at least two new states to explain the measured neutrino masses and mixings. But if we assume that only one of them is light enough or mixes strongly enough with the standard model, we can simplify the phenomenology in a 3+1 scenario. So why the GeV scale? So for instance, no extra hierarchy problem. The Higgs hierarchy problem is not worsened if neutrinos are at GeV scale in contrast with heavier neutrinos. They can also be a feasible solution for the Baryon symmetry of the universe by leptogenesis, which I show in this plot, and all the scatter points are the regions of the parameter space of the mixing and the mass in which the observed Baryon symmetry of the universe is reproduced. And most interestingly, if neutrinos have a mass of this order, they can be probed at terrestrial experiments, such as beam dams, big searches, or colliders even. So an especially interesting playground is going to be the near detector of neutrino oscillation experiments, such as DUNE. And this is a sketch of the process that would take place. Protons impinging on the target, producing a bunch of charged mesons, which could decay into heavy neutrinos by an insertion of the mixing. And then these new particles could travel hundreds of meters and decay inside a near detector into standard model particles, which could be detected also by an insertion of the mixing. So as I will show you in a minute, the near detector at DUNE will be able to probe wide regions of the parameter space of the heavy neutrinos in terms of their mixings and their mass. So taking into account the energies we are talking about here, I think I cannot move my slides. Can you see my slides moving?
No, we don't see it's advancing.
All right, give me a second. Can you see it now?
No, we don't see the slides yet.
All right, sorry, give me a second. All right, how about now?
Now we see the slide, yes.
You see the slide, right? Okay.
Yeah.
Okay, sorry. So coming back, taking into account the energies we're living at, we need to compute the interactions between mesons and the heavy neutrinos. And in order to do so, we have developed a low energy effective theory to take into account the meson interaction. So we have integrated out the W boson or the Z boson, depending on the charge or neutral current. We have introduced the hadronic matrix elements, which are parameterized in terms of the meson decay constant and its form momentum. And we have translated that for momentum into a derivative which acts on the lepton current. And if we assume that everybody is in shell, we can apply Dirac's equation, and we get to the operator you can see down here, which is a Yukawa-like coupling in terms of the mass of the leptons. So this is the case for a charge pseudoscalar. We have done the similar things for a neutral pseudoscalar and for vectors with similar results. But in the case of vectors, there is no for momentum, and thus the operator is just a QED-like vector captain. So we have implemented these interactions in fine rules, enlarging the neutrino sector, introducing the new guy in a 3+1 scenario. We have also included all the mesons with masses up to 2 GeV. And this way we can compute events in which the heavy neutrinos are produced and decay via meson interactions, and also in full leptonic processes, such as the ones in the standard model, which are, of course, depending on the mixing of the heavy neutrino. And okay, so my slides froze again. Sorry for the inconvenience. Give me a second. All right, so yeah, we have implemented this interactions in fan rules, and then in MATGraph to compute heavy neutrino production and decay events to estimate the sensitivity of the Dioneer detector. And our results are a thick green line, which compared to the gray shaded regions, which account for the existing bounds, are going to be potentially improving current bounds. And interestingly, we'll be able to probe very small mixings, such as those predicted by the type 1 seesaw mechanism. And we have computed here results associated to 7 years of data taking at a 90% confidence level. So that's all. And my conclusions will be mainly that our heavy neutrinos are important in many extensions of the standard model, which account for measured neutrino masses. And they can solve several problems of the standard model if they live at the GeV scale. And they can be experimentally proved as at near detectors of neutrino isolation facilities. And in particular, in Dune, the near detector will be able to probe very small mixings. So that's all. Thanks for your attention. Check my poster in Indico and hit me up on Slack for any questions.
All right. Thank you very much, Manuel, for the nice presentation. I have time for one question from the audience. Please use the raise hand button. I do not see any questions. Second call. Now I do see one. Felix, please go ahead, Felix.
I have one question. So how would you distinguish in the Dioneer detector an decay of a long-lived particle and an interaction from a neutrino? Wouldn't they look somewhat similar?
Yes. Well, we have not performed detailed detector analysis, but I would guess that depending on the detector, you can maybe reconstruct the decay products and hopefully try to reconstruct the mass of the heavy neutrino. I think it would depend on the decay channel, whether you have something invisible in the end or not. Because, for instance, the heavy neutrino can decay into a pion electron, which is completely visible, but it can also produce neutrinos in the final state. So I guess it would depend on the decay channel, probably. Anyway, a proper detector simulation will be needed with background, which we haven't done. So to answer to your question properly.
Yeah, and the near detector is filled with liquid argon as well?
Yeah, it's liquid argon.
Thanks.
Yeah, all right, thank you. So I do see a second question. I would like to entertain a second question as well. Victor, hopefully this question is short. Go ahead, Victor. Are you there, Victor, to ask a question? We could not hear you, Victor.
It seems that there are problems with the microphones. I would suggest to go on.
Yeah, so I'm sorry about that, Victor. So as Balin said, you can connect to the Slack channel. So let's move on to the last talk in this PhD forum. It's going to be given by Srirupa Chongda. The topic will be flavored leptodynamics and type 2 seesaw mechanism with the 2 Higgs triplet scalars. Srirupa, please go ahead.
Am I audible?
Yes, go ahead.
Okay. Can you see my slides?
Yes, we can.
Okay. So, myself, Shrirupa Chomdar. I am pursuing PhD in National Institute of Technology, Rourkela, India, under the supervision of Professor Shashmita Mishra. My topic is flavored leptogenesis and type 2 seesaw mechanism with two Higgs triplet scalars. As the name suggests, I'm going to talk about neutrino mass generation through type 2 seesaw mechanism and with two Higgs triplet scalars, and we have estimated the baryon asymmetry through flavored leptogenesis mediated by triplets. We have extended the standard model of particle physics by introducing two triplet Higgs scalars T1 and T2, each with hypercharge 2. The neutral component of the triplet scalars acquire Wacom expectation values omega 1 and omega 2, and omega 1 we have chosen omega 1 to be complex here. Omega 1 and omega 2 are bounded by the rho parameter, and they are much smaller than the standard model Higgs Wacom expectation values. We have chosen the masses of the triplet scalar to be hierarchical, and the lighter triplet scalar is chosen to have mass around 10 to the power 9 GeV. The extended Lagrangian consists of the kinetic term and the Yuka interaction term mediated by the triplets. The triplets undergo Yuka interaction with charged bileptons, and these leptons belong to different flavor generation. This is the reason we need to consider flavored leptogenesis instead of unflavored leptogenesis. The coefficient of the lepton number violating trilinear term present in the potential is also made complex. The neutrino mass generated through the contributions of triplet type T1 and T2 are presented here, and as we can see that the tiny neutrino mass generated by this process is inversely proportional to the heavy triplet mass, thereby exhibiting the typical seesaw behavior. We have introduced the 2-0 texture B2 in the neutrino mass matrix to increase the predictability of the model, and we have calculated the neutrino mass matrix elements keeping in mind the upper bound on the sum of the neutrino masses, and we have calculated the neutrino mass matrix elements by using the latest neutrino oscillation parameter data. And as it seems from the parameter space study that this texture B2, it disfavors inverse hierarchy of neutrino mass. To obtain a non-vanishing CP asymmetry, we need to have at least two heavy triplet scalars in the model. And here we have shown the tree level and one loop decay diagrams of triplets, where we can see the triplet has two decay modes. It can decay into charged bileptons and into standard model Higgs. In order to confirm purely flavored leptogenesis, we have chosen the branching ratios of triplet scalars conveniently, so that we can say that triplets are coupling predominantly to the leptons instead of to the standard model Higgs. And we have calculated the fully flavored CP asymmetry parameters for each flavor generation. After solving numerically a set of fully flavored Boltzmann equations, we obtain the lepton asymmetries, and we plot those lepton asymmetries for each lepton flavored generation with a factor Z, which is the ratio of triplet mass and the decreasing temperature of the universe for different sets of branching ratios. And finally, we obtain the present time lepton asymmetry, and we convert it to the baryon asymmetry by Sphaleron process. Here C is coming from the sphalerons and A is coming from the chemical equilibrium calculations, and we achieved baryon asymmetry of the order 10 to the power minus 10, which falls within the permissible range suggested by the experimental studies. Here I want to conclude that the type 2 seesaw mechanism is capable of estimating baryon asymmetry, and it can also generate tiny neutrino mass. So it acts as a bridge between baryon asymmetry or the matter-antimatter asymmetry of the universe and the neutrino mass. So future work can be done using different values of triplet scalar masses, which is below 10 to the power 9 GeV. And we have not seen any particular changes in the result taking different values of branching ratios. So I think that the hierarchical branching ratios are not mandatory here. So I want to end my presentation here. Thank you so much.
Thank you very much, Sri Rupa. Please go ahead and raise your hand for any questions from the audience. Yes, I see one. Alain, please go ahead.
I see also Stefan, so let Stefan if you wish, because I'm the chair. So I yield to Stefan Lavignac, and if you give me time, I ask after, otherwise not.
Thank you, Bill, and thank you for the nice talk. I just have one question. Did you, in your study, did you use the Boltzmann equation taken from the paper you cite by Gonzalez, Felipe et al.?
Yes, yes, yes.
Okay, because I think there is a Neros term in those equations, so which I don't remember which one it is. So I will put a reference to one of my paper in the chat where we comment on these equations. So I think there is one term that is not correct.
Okay, okay, thank you so much. I will look into it.
Alain, would you like to ask your question too, if this is short?
Yeah, very short. I think in slide 6, you showed a particular texture that you chose there.
Yes.
Is that motivated by symmetry, and how much the result change if you go to other textures? Just a brief idea.
Actually, primarily, we have chosen this texture B2 because in the context of two triplets, the other texture 2-0 textures are not compatible with the latest neutrino oscillation parameter data, and that is why we have chosen this texture B2. But we are still learning and checking everything.
Okay, very good. Thank you.
It is not final.
All right, thank you. So please join me to thank all these 5 student speakers for the wonderful talks. Job well done, congratulations. So let's move on to the last item. So we have the last plenary talk by Felix Klein. He's going to tell us about the physics with the Ford LHC neutrino detectors. Felix, please go ahead.
Okay. Can you hear me and see the slides?
Everything works fine.
Perfect. Okay. Yeah, thanks a lot for inviting me to this nice conference and giving me a chance to talk about our work and even more our plans for the next couple of years on physics with forward neutrino detectors at the LHC. Before I want to go into the physics, let me just show what I had to go through to attend this conference. You might think that we live in a time of virtual conferences which require neither traveling nor approval, but this is not true, at least not at national labs at the US. They came up with these workflows that I had to go through, and I just find it interesting to see that it's not just Germans who come up with unnecessary bureaucracy, but that this also happens in other countries. Anyway, let's go on to the physics. So I will talk about neutrinos at the LHC, which is something that we all know exists, but none of us has really thought about it or cared about it until very recently. The idea of detecting neutrinos at the LHC, however, goes back many, many years to work by de Ruyula in 1984. So the idea is that there is a huge flux of pions and kaons and other light particles that go in the direction of the proton beam. So the beam remnants hadronize and produce a large number of mesons that then decay into neutrinos. So I show here an example. This is the region around the Atlas interaction point. You see all these the LHC tunnel structure here, and in red I show the the direction of the beam, or the beam collision axis, how I would call it. And along this direction, a large number of neutrinos and a really intense beam and strongly collimated beam as well of TV energy neutrinos is produced. And as neutrinos don't get deflected and don't interact, this beam would just go straight. And you will see that there are 2 locations here on the right and here on the left where one can already, with the existing tunnel structure, put experiments to directly placed into this beam, harvest the beam, and perform physics with it. Well, as I said, this is an old idea, but nothing has happened until rather recently. In 2018, the Phaser collaboration put a 30-kilogram immersion detector in this side tunnel here, TI-18. It connected the SPS, so the pre-accelerator, with the lab tunnel in lab times. It is not used anymore during LHC because they built a bigger connecting tunnel, which is this one here. So this side tunnel remained unused until recently, and we have put this, this rather small immersion detector in there directly into the beam. And very recently, only a couple of weeks ago, we announced the first neutrino interaction candidates that were reconstructed in this immersion detector. I want to stop a moment, just think about it. We have these giant detectors, Atlas CMS, but also previous experiments, let's say D0 CDF, that operated for years and have many tons of mass, that where no neutrino interaction was detected in them. And now this little 30-kilogram detector with only a couple of weeks of exposure could actually accumulate some of them. I find that rather amazing. Okay, of course, we would like to have something better than this quickly assembled pilot detector here, and that's what's going to happen in the next one of the LHC. Actually, there will be 2 experiments to perform neutrino physics. One is Phaser New, which will be in this side tunnel TI-12 here on the right. The trench was thick so that the experiment will be directly on axis and where it accumulates most neutrino events. And one expects order of 1,000 electron neutrinos, 10,000 muon neutrinos, and even 10 tau neutrino charge current interactions occurring inside this immersion detector at the front, which is then followed by a spectrometer, which was, mainly proposed to search for long-lived particles like heavy neutral leptons that we've just heard about, but could also help to further analyze these neutrino interactions. And then on the other side, there is another proposal called SND at LHC, which is located slightly off axis, has a slightly different detector technology, and will search for neutrinos there. This is doing, the Phaser detector was actually successfully installed already in the tunnel. You can see it here. You already saw it on the title slide. So here is the LHC beam with the protons going back and forth. And here would be the neutrino beam, or if you would like to think about more exotic, light and weakly interacting particles, also long-lived particles or dark matter. Okay. So this is our plan for run 3 of the LHC for the next couple of years. This will certainly happen. It's already interesting to think forward for the high luminosity LHC era, where it would, of course, be nice to build something even better and bigger and more dedicated and more powerful to collect even more neutrino interactions. And the idea that gained some momentum very recently is the idea of a forward physics facility, so a dedicated place that could house a suite of experiments to, both use this high energy neutrino beam or also probe dark matter or long-lived particles at this location. And here I just show 2 ideas of either increasing the size of the cavern here or even building a new cavern on this side to house those experiments. This includes experiments for long-lived particles, new neutrino detectors, detector for milli-charged particle or liquid argon detector. And we're currently writing a physics summary to summarize the physics potential of experiments, neutrino experiments at the LHC. And if you would like to have more information, I put some links down here. A letter of interest that was written for SNOWMAS and a link to 2 meetings that were focused on this topic. Neutrino experiments at the LHC will help us to greatly enhance the LHC's physics potential for BSM physics searches, neutrino physics, and QCD, and I will just show you a couple of examples in the rest of the talk. So let's start with neutrino physics. The neutrino beam at the LHC is very broad and very high energetic. So I showed here the neutrino beam profile as a function of energy, also in comparison to other experiments. And you can see that its main feature is that it's more energetic than any of those other experiments, as we would expect, reaching up to TeV energies. Originates from pion, kaon, charm decays. I show here on the right both the energy spectrum of neutrinos interacting and the rapidity spectrum, or if you want to think about it differently, how far displaced it is from the beam axis. And yeah, we can really see that this is for a 10-ton detector at the proposed forward physics facility with a full LHC luminosity, and you can see that there's a quite large number of flavors of neutrinos of all flavors. What are the interactions? So I'm based on suggestions, I made this plot here showing the invariant mass of the hadronic system versus momentum transfer. We can see that really most of the interactions are deep inelastic scattering, or can be described by deep inelastic scattering. Neutrino quark goes to lepton quark. The typical multiplicity of event or of particles in the final state is rather large. So in the DIS regime, it's typically order 10 or so. But there's also this regime down here, so shallow inelastic scattering, which could be used, for example, to essentially probe the region that's more relevant for low energy scattering, where we might worry about quark hadron duality, but probe it from the high energy side, in contrast to the other low energy experiments, which would probe this region from the low energy side. What can one use it for? I just give you one example here to measure the neutrino cross-section and the unexplored TeV energy range for all flavors. So here I show the neutrino energy. Here's a cross-section divided by energy, which is roughly a constant. The gray shows existing constraints for neutrinos and for anti-neutrinos when the distinction is available. And in these colored error bars, I show what either phasor or deturing 1.3 or a 10-ton detector at the high luminosity LHC could do. And we can see that they really extend these measurements to higher energy, or fill the gap in the case of mirror neutrino to the ice cube measurements. Particular phasor already detect 10 tau neutrinos, which is similar to Donut and Oprah, and thousands of tau neutrino events are possible at the high luminosity LHC. So this would be essentially a scenario where we can probe the properties of the tau neutrino and perform tau neutrino precision studies with an already existing beam. We could also look, this previously I showed the inclusive interaction cross-section, but one could also look at more exclusive channels, for example, at low energy channels like neutrino, neutron goes to muon proton. Quasi elastic scattering, and also constrain those channels as shown in this plot here. We expect a sizable number of events here as well. We can also do a variety of new physics interpretation of these measurements. So for example, use it to constrain the standard model EFT coefficients describe or including neutrinos, essentially for fermion operators, as done in this work here for charge current interactions, and in this work here for neutral current interaction, where it's also called neutrino non-standard interactions. Or one could think about neutrino oscillations. Of course, there are no standard model neutrino oscillations, but one can think about a multi-EV stereo neutrino, so similar to what's probed at the short baseline neutrino experiments. So this setup, the LHC, could be a short baseline neutrino experiment. Going on to QCD and cosmic rays, the forward particle production in general is rather poorly constrained by other LHC experiments, purely because they don't cover this region They cover the transverse region. However, the neutrino flux measurements in the forward direction will help us understand, improve, and validate these neutrino fluxes and the underlying event generators. So here I show one example. This is the neutrino flux splitted by production modes. Oh, this is the energy here on the x-axis, sorry, for electron and muon neutrinos at phasor, where the different color shows the different production modes, pions, kaons, d mesons. You can see two things. At first, different regimes of phase space are sensitive to different production modes. So for example, here at low energy, the pions dominate, while here at high energy, the d mesons dominate. And we can see that different generators shown here as different line styles show some differences. So for example, here, this is probably about a factor of 2. And as you've seen on some of the previous slides, the expected statistical uncertainties will be much smaller. So one, with the data available, one will then be able to constrain these models, these hadronic interaction models, and improve the generators. This is particularly interesting for forward charm production. So this is a process where, for example, we produce charms in gluon-gluon fusion. So charm hadronized to a d meson, decays into into a neutrino, and all of this typically happens. So this is a process that can be described by perturbative QCD in contrast to, for example, forward pion production, and it is sensitive to QCD at very low x. So I show this here in a cartoon on the left and more quantitatively on the right, the landscape of the gluon PDF, momentum transfer versus momentum fractions. The shaded regions show all the, regions where data is available currently, for example, from the LHC or from HERA. And these dots here show correspond to events that lead to a neutrino going through phasor. And we can see that it's sensitive to very small x gluons, which are currently far not probed and far away from anything that has been probed. Of course, there's also high x gluons, so one's typically low, other one is high x. So this could allow us to test the transition to small x factorization and constrain the low x gluon PDF. And you can also see that this is exactly the regime where we expect gluon saturation to occur. And we can, thank you. We can probe it, possibly probe it with this experimental setup. And we could also potentially probe intrinsic charm. Why is that interesting? One example where this is really needed is cosmic ray physics. So what I just called the forward charm production at IceCube would be called the prompt atmospheric neutrino flux, which is rather poorly constrained. IceCube can just give a kind of upper limit on it, but it's one of the main backgrounds for the extragalactic neutrino searches. And it would be really nice to have data available that will help us to constrain it. And that's exactly what we would probe with these forward neutrinos from charm production. There's also another cosmic ray motivation, and that's the Murum problem. So cosmic ray experiments have reported an excess in the number of muons over expectations, which were computed using extrapolations from hadronic interaction models from LHC data. And this is at a few sigma level currently. So essentially what has been done is one wants to measure the composition of cosmic rays, and this can be done either by the shower profile called Xmax or this muon content. What has been found is that both measurements disagree, and disagree so much that it's essentially impossible to really extract what was the composition of the cosmic rays, or was it iron or proton, at this level of disagreement, and therefore distinguish different cosmic ray sources. So for the success of this cosmic ray physics program, it would be very good if we can eliminate uncertainties for these hadronic interaction models, so that we can finally perform this measurement with good accuracy. So this data from the LHC would be quite crucial. Another application for QCD that one could think about are probing PDFs using neutrino scattering. That has been done by many previous neutrino experiments, for example, NUTEF. This could be used to probe, for example, nuclear PDFs, which have rather large uncertainties. Here I show one example for the strange PDF, and you can see how large the strange PDF uncertainties can be, especially in the low X regime. But one could also, probe especially for the strange quark, measure the strange quark content of the proton, where there exists tension between previous measurements, for example, from neutrino measurements and Atlas measurements, and one could probe it using the process neutrino strange goes to lepton charm and then takes the charm in, for example, the margin detector as slightly long-lived particle. It travels a couple 100 microns, which is detectable on these detectors, and then extends the reach towards higher energies, meaning lower X or higher Q in the PDF landscape as shown in this plot here. Okay, let's go to the last example of physics that could be probed, and this is BSM physics. Probing another invisible particle or potential invisible particles, dark sector particles, either dark matter or the mediator. Let me just, for concreteness, provide a toy example that is a dark matter charged under a U1 dark gauge group, so a dark photon, which then also couples to the standard model via kinetic mixing. So this is our Lagrangian that we consider. And then the phenology of this model is very broad, but depends on the masses, roughly speaking. So if the dark photon is heavier than 2 times the dark matter mass, it will mainly decay into dark matter. And essentially, this dark photon could be produced, for example, in pion decay or in eta decay or ion production, and then decays into dark matter. So we produce an energetic dark matter beam at the LHC, directed at these neutrino experiments I just mentioned. If it's lighter than 2 times the dark matter mass, it can't decay in dark matter. It will decay into standard model, but the typical kinetic mixing is very small, so the particle is long-lived, and we have a beam of long-lived dark photons directed at the neutrino experiments. If the dark matter mass, dark photon mass is 0, the dark matter essentially becomes millicharged. So we will have a beam of millicharged particles directed at the experiment. Thank you. So let me just go through these 3 examples very quickly and then conclude. Starting with the dark matter beam, which could then scatter in the neutrino detector. So as I said, the number of high energy mesons are produced in the forward direction, which are produced, for example, in hadronization of beam remnants. Then these can decay into a dark photon. For example, pi 0 goes to an A prime, which then decays promptly into dark matter and scatters on electrons in the target. And the typical energy is of order 1 to 10 GeV. So the momentum transfer is typically very small in this case, which is very different than for possible backgrounds, for example, neutrino scattering on electrons, which has typical energies of TeV. So those are actually distinguishable. Here I show a plot that my colleagues made. See this paper for details, showing the dark matter or dark photon mass versus the coupling. Everything that's gray is already excluded. The black line here is the dark matter relic target line. And this yellow shaded region with blue contours is the is the sensitivity of LHC neutrino experiments. And one can see that they probe the interesting region between the relic target line and the existing constraints. Okay, going to the long-lived particles. So as I said, if the dark photon is lighter than 2 times the dark matter, it can only decay to standard model particles. Couplings are small, otherwise we would have discovered it, making this particle typical long-lived. This is the dark photon landscape, coupling versus mass again, with existing constraints, for example, from prompt searches, prompt dielectron resonance, for example, at NA48 or bar. The in below this line here, so this line corresponds to a proper lifetime of a centimeter, or on the LHC frame at TeV energies, 100-meter lifetime. This particle is rather long-lived and can actually travel the 500-meter from Atlas to these neutrino detectors, or phasor as a long particle detector. And one would be sensitive in this regime to search for displaced decays, as shown by these lines here. There are also existing previous constraints from beam damp experiments, for example, as well. This is just one example, the dark photon. For many other models, and for details of this, I refer you to our physics case for phasor, where this was already investigated in quite detail. Finally, for milli-charged particles, if the dark photon mass is essentially zero, the dark matter becomes milli-charged, and the signature would be a minimum ionizing particle, but with very small DEDX. There's actually an LHC experiment proposed to operating even to search for those, a Millikan experiment near CMS, which is essentially in the transverse region, so at a 45-degree angle to the beam. But it was noticed in this paper here that if one would move it in the very forward direction, one could increase the signal rate by about a factor of 100. This is shown here. So this is the mass versus the coupling. And one can see that we called this experiment Formosa if it's moved in the forward direction, and one can see that the reach here compared to Millikan increase quite a bit. This example could also be dark matter, an example of very strongly interacting dark matter above the direct detection bounds, where the dark matter wouldn't even be energetic enough to cross through the Earth and reach our underground detectors. But of course, when produced at the LHC, it would be very energetic, and that would not be an issue. So we could probe this very interesting kind of blind spot regions between dark matter bounds and then the collider bounds. Okay, let me quickly conclude. So there are two new experiments at the LHC dedicated to neutrino measurements. That's phasor and SND at LHC that will start operating soon. But that's not the end of the story. These experiments also paves the way to forward search and neutrino program at the high luminosity LHC, which we should start planning now, so that it can start measuring at the high luminosity LHC, which is only in 6 or 7 years or so. And this opens up many opportunities for neutrino physics, BSM physics, QCD measurements, and so on, extending this LHC physics program. And we would like to invite the Invisibles community to help us better understand and explore this physics potential of this program. I hope that you have some ideas or some models in mind or some other applications, and share your expertise with us. Your input is very welcome. As mentioned, we are currently writing a physics potential summary for this program. So if you have some ideas, then you can contact me directly or visit the workshop that occurred on this topic last week for more information. And with this, I want to thank you for listening, and curious if you have any questions. Thank you.
Thank you very much, Felix, for the very nice summary for the physics opportunities at the Ford LHC. So I think we can open the floor for some questions from the audience. I see one already. Alvaro, please go ahead.
Yes, thank you. Thank you for a very nice talk. I have a comment and a suggestion.
Mm-hmm.
The comment is that it isn't your fault because you were not born, probably. But if this kind of physics had been pursued when it was proposed, the neutrino tau would have been discovered much before the time when it was discovered, and one would have been able to save a lot of money by not sending neutrinos to the Gran Sasso. So physics would have been very different if this sort of neutrino physics from colliders, someone had paid attention to it. That was the comment. The suggestion is the following. I don't know whether this is possible, but if when you see a neutrino interaction in one of these experiments, you could send the information fast enough to the collider experiment that produced the event that gave rise to the neutrino. They could keep that event, not throw it away as they do with most events, and analyze it. For instance, if it was due to the production of a charm, anti-charm pair, they could maybe catch those charm particles, at least one of them, and one would this way be able, I believe, to understand better the production of, among other things, heavy flavors in the forward direction. That was my...
Yeah, that's a very good question. I think the limitation is triggering, so they only store the events for a certain amount of time, and I'm not exactly sure if they store it just long enough.
But what I'm suggesting is that you think about it.
Yeah, yeah.
Maybe,
no, this is actually a good point. We were thinking about it, and we haven't really found like the ideal case where this would be super helpful. And I'm not sure with charm production if the, in this case, Atlas would really see the rest of the event very well. But this is something that we should probably study, just run a couple simulation and see where the
maybe LHCb
production
could do it. It could be that LHCb is more adequate for this kind of thing, but you're not planning an experiment downstream from LHCb, at least for the moment.
Yeah, LHCb would probably be better for this. I completely agree. Yeah, thank you for the comment.
You're welcome. Thank you for the talk.
Yeah. All right, thank you both. So let's take the one more question. Thomas, please.
Yes, hello. So my question is about the sterile neutrino. You mentioned the search for sterile neutrino. And I mean, my question is, do you have an idea of the sensitivity which you can reach there? I mean, I guess it has to do, the question is, how well do you know the beam? How well do you know the flavor composition of your initial beam and so on? I mean, is this all under control? Because in this high mass range, there are some limits. So you need to be precise if you want to address something there.
Yes. So for sensitivity estimate that we made only a couple of years ago, I would just refer you to this paper here, our phasor physics case, where we have some reach plot. It's what we found is that typically uncertainties of the order of factor 2 that typically are there in production models don't make a big difference, since these plots here are always log scale in each dimension. So increasing the number of events by a factor of 2 would only move the lines by a millimeter in either direction. So that turns out to be somewhat not so sensitive, but then you might say, well, you say a factor of 2, but if you look at the forward charm production uncertainties here, this is for neutrinos, not for heavy neutrinos. It might actually be quite a bit more than a factor of 2 in the very forward direction. So yeah, one really should study the forward charm production more carefully before one can really make reliable bounds. I think right now, even for BSM physics in these log plots, there would be quite some uncertainties due to production. You're right.
No, but you mentioned sterile neutrino oscillations, right?
Oh, sterile neutrino oscillations. Sorry.
Yes, exactly.
I thought about heavy
measurement. No, I mean,
okay.
You need to be precise at the percent level.
Yeah. This is, of course, even more true. Their factors of 2 matter much more. In general, all these BSM applications would only really work once the standard model uncertainties are under control, which they are currently not, but I hope in 10 years the situation would improve. So these uncertainties here, we actually included uncertainties from different production models and showed this as rough uncertainties. If this is accurate or not, at the moment, I don't know, but as you can already see, this will heavily influence the reach of the search. So this is something that needs to be studied and is currently under investigation by several groups, actually. So I think we will make progress there.
Yeah, thank you. So I think we run out of time. Yeah, we have overrun by more or less 10 minutes. I think we should conclude this session. So thank you very much to all the speakers And let's take a short coffee break. So we will resume the next session in the hour 17 for the Central European time. So please come back and see you soon.
Okay.
Thank you.
Sorry, Berlin, we ran out of time in the
No, it's
10 minutes.
perfect. It's perfect. And now also they can see in rolling time the posters that they can go to the Slack session and Indico and then choose their favorite and vote before Friday. You see, so the posters are flashing, but of course to read them carefully, go there. There is also videos. No, you did perfectly. Thank you very much, Tao Han. Thanks a lot.
No, you're welcome. Thank you for the invite. It's a lot of fun, and it's quite impressive to see the student talks, and they are very much on time, and they are seem to be very well presented. It's a good idea to do so.
Some very often you get much more than from the senior talks. They give you the idea, the question, some result, and then you have the curiosity to go, this is working very well. And as you say, they tend to be amazing, these 5-minute talks of the students. And they are very good. That gives them full exposure, so to say. So
exactly.
Okay, so thank you very much. And
you're welcome. So I hope to see you sometime in person before too long.
Yes, me too. Either here, this side or there. Let's hope. I'm trying to go to the States soon, but the moment is forbidden, as you know.
No, it's not very advisable yet. I think once you have 2 shots, you'll probably be okay. But still, we don't want